so this test 3-1, 3-2, 3-4, 4-1, 4-2. It's really just 3 topics. Let's discuss that. Topic 1, acceleration. That's 3-1 and 3-2. Topic 2, free fall with acceleration. That's 3-4. And then the third topic, vectors, which is 4-1 and 4-2. So it's really 3 topics. Now, keeping in mind, you have 2 skills for math you need to know for this test: quadratic formula, trigonometry. Quadratic formula, trigonometry. Those 2 things are also necessary. So 3 new topics, 2 old mathematical concepts. What I'm going to do is start with an example from 4-1 and 4-2. I took another approach. I felt that some students were really struggling with 4-1 and 4-2 based on feedback I was getting from you and based on the quick 20 minutes this morning. Those were all the questions that were on that. So I'm going to go through an example of a problem with a different approach, a tabular, like with a table approach. So those of you who like using tables and like having like organized devices with math problems, this will really help you a lot. So if you've been struggling just to visualize what's going on, this table approach might be a good way to think about it. So let's say, and I'm gonna make this problem different from the other classes so that later tonight, if you want to review and study, what video should you watch? The other class, not yours, because you already wrote all this down. So it's going to be a different example of the same topic, so you could practice the other class's example tonight, vice versa. They could practice your example tonight. So let's say that an object starts moving west. Which way is west? Which way is west? Good. You're pointing. That's fine. Left. So an object moves west a distance of 2 miles, stops, then moves southwest at an angle of 15 degrees for 1 mile. Try and visualize what that should look like. Southwest at an angle of 15 degrees for 1 mile. So right away, you start here as this is your new starting point. From the starting point that the white dot is here. West would be left. Southwest would be down here. Try to visualize if you have to. Use the pointer. So this is like your new origin right here. This is west. So southwest would be to the west and then south of that. To the west and then south of that. So if it's at 15 degrees southwest, it means that the object is doing something like this. And it's only I should make that a little shorter, because it was only 1 mile, so it's reasonable. Should be about half the length of the other one. Okay, so again, an object moves 1 mile, 15 degrees southwest. John, go ahead.
Okay. 2 things.
Yeah.
I don't know if this is a question, but why is the line connected to the first point of the west and not the last?
So yeah, here's how I want you to think about it. I want you to think about this as the origin on an XY axis. Imagine this is the Y axis, okay? And this is the x-axis. The only way to go southwest would be go along the x-axis and then down below. So I extended this dashed line over here just to give me a little bit of room. It's called the construction line. It's just there so I have a reference point. It's not really a line. Okay? Second question?
Second question was about the dash line.
Oh, okay. So yeah, again, extend it this way. And then again, to go southwest, you go west, but you go south of that. That's how you know where to go. That is the third quadrant. Remember, if you need to write this down, northeast, northwest, southwest, southeast. Just write those quadrants down. Maybe it'll help you remember which way you're going to go. And remember that whenever you stop, you're starting over. So this person moves, stops. They're starting over. Here's your new origin. They go here, they stop. Now we're starting over again. Now this is the origin again. Let's say that the person now moves 3 miles at an angle of 40 degrees southeast. 3 miles, angle 40 degrees southeast. So here's your new origin, where I'm pointing to. Which way is southeast? I go east, and then I go south. So south of east. So I'm down here. So I know it's going to be 60 degrees, so let me draw a little construction line again. And I'll put this vector here at an angle of 60, make it look much bigger. And I know that this is 3 miles in length, so maybe I'll make that a little bit longer also. So again, the numbers 1, 2, and 3 are not the segment in like order. It's the length, right? So this is 2 miles. This is 1 mile and 3 miles. Okay, those are all miles. So our goal in this problem is going to be to figure out the overall displacement of the object. The overall displacement. Now, I want the magnitude and the direction of that displacement, which simply means I need to know the length from start to finish and what angle we're traveling at here. What is the angle? How do we know the actual orientation? Okay, so connect your starting and finishing points. Let's do that with a different color, maybe green. Let's see how green works in this. Can you see that? Yeah. All right. So that's the overall result that we're trying to figure out. Always, from start to finish. Start was up here, right there. That was starting point. Finishing is right here. Again, 2 miles west, 1 mile southwest at 15 degrees, 3 miles southeast at 60 degrees. Okay, that's my overall. Well, how do I figure out that value of r? To do that, I need to think of it as a triangle. Think of it as a triangle. So think of r from here to here as a triangle. Do you all see how this is really a right triangle? If I could figure out the overall length of the base of the triangle, the overall height, I could use Pythagorean theorem to give me the overall displacement.
Didn't you just add, like 3 miles?
No, because they're at angles. Remember, they're at angles. If they were all perpendicular, it'd be easier. If I said I'm going up 3 miles over 2, sure, Pythagorean theorem right off the bat. Or up 2 miles over 2, up 3 miles, then the 2 and the 3 you could add together, yes, and then you have 3 over. But these are at angles. The minute they're at angles, you need, remember the things they're called components. You need to break them into their pieces. So see the 3 mile and the 1 mile segment? Those have to be broken up. The 2 mile segment, although like you said actually, you don't have to worry about it. It's all west, right? 2 miles is directly west. There's no angle for the first part. So what I'm going to do is show you a table, and the table is going to organize all of this data and allow you to sum these values together a little bit easier. Okay, so let me point out what we're physically doing first, and then I'll start using the table so you can all see it. Why are these in pieces like this? Okay, so I'm going to point. So just watch for a little while. Where is this coming from, by the way? Which one is it? It's this one, yeah. Could you mind real quick? Yeah. It's coming off the little model bridge thing there. So you guys can see, that's what I'm saying. All right, so ready? So here's the starting point. Let me talk about it. So, thank you, John. That's perfect. That's good. So yeah, so this person is moving west only. Now, when this person moves this way, this is southwest, right? They're really moving west and south. So there's really another little triangle right here. Visualize, please. There's really a triangle here. I need to know how far west, that's 2 miles. Then I need to figure out how far west this part goes, how far south this part goes. Then this next part I have to figure out how far east does it go, and how far south does this part go. So there's a lot of pieces I have to put together. So if I were actually figuring this out, I have to figure out all the x's and the y's separately. So this x is -2. Why is this -2, this x?
Because military west.
Yeah, west. West is negative. Then this x will continue to be negative until I get to here. And then when I move back down to here, this x I have to cover this way will be positive. So whenever you look at each of these vectors individually, you could draw its own triangle. That's kind of what I was doing in class, but I felt like that confused a lot of people. So I'm going to take a table approach. So if we take a table approach, we go ahead and list 4 topics. We have vector length. We have the angle. We have the x component and the y component. Now, each of these vectors has an angle, whether you realize it or not. The first one has an angle also, but I don't care about the angle if it's north, south, east, or west. I don't care about the angle. What's the length of the first vector? What is its length, everybody? The length of the first vector. Go ahead. Just 2, right? Just 2? Well, just the length I'm asking for, just for a moment. Just give me the length for just for a second. Okay, give me the length of the second vector. Lauren, the second vector, what's its length? Just the length of the vector. Start your path. Here's the first vector. Here's the second vector. Here's the third. 1. And the third vector, its length? 3. So those are the length of all the vectors. Again, I don't care about the angles right now. I'm just listing the lengths. 2 miles is the first length. 1 mile is the second length. 3 miles is the third length. Those are the vector lengths themselves. If it helps you and you want to use decimals because the 2, 1, 3 is messing you up because of the order, pick decimals. It doesn't matter. The angles. Now, the first one, does that at any angle? It's only west, right? So let's put a little X here, like something that shows that there is no angle here, really. There's no angle that's going to be listed. How about the second one? What's the angle for the second one? 15 degrees. And where does he get that? It's right here, 15. How about the third vector? 60, right here. So the reason I'm showing you this tabular approach is because some people, instead of drawing out triangles and having trouble understanding that, might find this approach easier because you can simply practice it and it becomes rote memorization afterward. Okay, you can practice it more and more. I know some of you like to practice your math skills a lot and it makes problems easier. This is an example of that. Now, you are wondering, what are we doing with these parts? Well, if you recall, we talked about x and y having sine and cosine components to them. And we talked about how x is really the cosine of the angle times the vector, and y is really the sine of the angle times the vector. And I gave you a little hint, and I said, you know what? You guys should just memorize that it's alphabetical. X before y, cosine before sine. So these ones already, I know it's always going to have a cosine involved for all of them, where there's angles. Here there's going to be a sine involved for both of these, where there's angles. Now, all you have to do is put the vector length in front of the actual argument first. So start by putting the vector length of 1 and 1 here, and 3 goes here, and 3 goes here. So again, take the vector length, put it in front. Take the vector length, put it in front. Then you put the angles after the trig function. So this angle is 15 degrees, 15 degrees, 60 degrees, 60 degrees. So I'm literally just using this table to organize my data so far. Cosines are always going to be here, sines are always going to be here. Why am I not filling in the first row? There is no angle. What should I fill in the first row? Is the first motion in the x or in the y? The first motion, is it in the x or in the y? The object starts here and walks 2 miles this way. Is that x or is that y? Which one is it? It's x. And is it negative x or positive x? It's negative x. So this simply is -2, and this is a 0 on the end. So when an object is moving either north, south, east, or west, and I don't have an angle involved in the problem at all, when there's no angles at all, I don't have to worry about it. So if it's only moving west, it's -2. That's that way. If it's only moving east, it's +2 over here. If it's only moving north, it's here, positive. If it's only moving south, it's here and it goes negative. Yes?
But I'm confused as to how you find the cosine of the 15-degree angle if you don't have any information on that triangle.
Well, you don't need it. You have a calculator. Type in cosine 15. You don't have to. Yeah, you're not going to have to worry about it anymore for this. Yeah. Okay, so let me explain what you're physically doing so you can see. This right here, well, we need to figure out sines in a moment, but let's keep going though. This 1 cosine 15 is this length of 1, and the cosine 15, that's that length right there. So am I moving from here to here? Ready? Watch. Follow. From here to here. I'm moving this way and then this way, right? This way is west or east? So that's going to be what sign? And then this way is south or north? So that's also going to be negative. Put those negative signs in. Negative, negative. The next vector, the 3-mile vector. Follow along the path, please, okay? So again, this is the motion you would actually take, but really the motion is this. That's what it really is. You all see what I'm saying right now? I keep breaking these into right triangles. This is the hypotenuse, but really you're going down and then over to the right. Down means what? In the y direction, negative. To the right, though, means what? Positive. So leave this alone as or write a positive sign. It doesn't matter, either one. Okay? Leave this as a positive because in the x direction, you're going to the right. Because the y, you're going down, that becomes a negative there. Yeah?
So what happens if you go east first? Then
If we went east initially to start this whole problem, this would have been a +2 to start right here.
no, I meant from like for the second triangle. From after you go south.
So right here?
Yeah.
So if I go east and then south?
Yeah, can you do that?
Of course, because vectors are commutative, remember? You could add this way, a plus b, or b plus a. You still end up right here, don't you? So it doesn't matter. Think about it. It'd be positive to the right, which is still positive here. And then negative down, meaning still negative here. So it does not matter which way you go. Okay, good question. That's a question that will come up on the test, actually. The order in which you add things does not matter, right? It's commutative.
So, well, but since like we're actually looking for R.
Yeah, we're not done yet, so let me get to that. So we need to now figure out the fact that, look, these x's summed together will give you this length right here. These y's summed together will give you this right here, always. I'll go into it if you'd like, but if it helps to just remember that if you add the x's together, you're going to get the horizontal part of the triangle. When you add the y's together, you get the vertical part of the triangle. And think about it. This is negative 2. It means you're going there. This number is how far you go there. This number is as far as you go all the way back over. So this is going to be summing two negatives and then the positive because you're coming back. So the answer for all of these will literally be whatever length this is. It will probably be negative because look, from start to finish, you're moving down in the y and left in the x. So there's probably going to be negative for both of these answers. So add together these three numbers. See what you get. So again, you're adding together the x values and you're adding together the y values. You should get a negative answer for y, 100%, because you're adding together two negatives. The x is most likely to be negative, but you can't assume until you do it. The diagram is like that.
Can I plug in my iPad? It died.
Again, make sure your calculator is on degree mode when you're typing this stuff in. Hit mode and just see that degree is highlighted. If it's not, go to a degree and hit enter on it. Yeah. You got it? That's right.
I just add that.
Well, I would do all this in one line. I would not type in all three numbers separately. So type in -2 plus -1 cos 15 plus 3 cos 60. You know what I'm saying? Add them all together straight down in your calculator. Do it all in one line on the calculator. When in need, put in parentheses. That's why I tell you guys, I don't joke about this. You have to practice with your calculator. So if you have it, you should be having it out right now and doing this. Again, -2 plus -1 cos 15 plus 3 cos 60. Yeah. Negative.
Yeah, I got -1.46 for x.
All right, I heard two of the same from the two of you.
X is
Negative 1.46.
Well, yeah. Yeah.
Is that what you get?
Yeah, that's what I got.
Okay. Check your work. Yeah, you could have made a mistake.
-2
Try it on your calculator, please.
-1 cosine 15 plus 3 cosine 60.
Yep.
Would you rather to -1.46?
1.46.
Yeah, if you want to round, I would wait till the final answer when you calculate r around r, because this is going to be, remember, -1.46 is literally this length right here. See that 1.46 I just drew on the diagram right there? That's what that length represents. It's negative because you're going to the left. Lauren? Agreed? Others?
I got 2.6.
But, yes, so agreed. And again, if you're gonna round, I'm not focused in this course about rounding and sig figs and stuff. It's just a waste.
That's what it always goes beyond.
Yeah, that's okay. Don't worry about it. Honestly, it's not what's gonna make or break.
For y, would you do sine 15 plus -3 or just -3 and then sine 60?
For the y value, I would type in my calculator -1 sine 15 plus parentheses -3 sine 60 close parentheses. So I would sum together each of these quantities in parentheses to be safe. Okay? All right, now I've got those two values. They're both negative because this object ends up going south and then west in the end. Goes south and then west. South is negative in the y, west is negative in the x. That's why both of these numbers are negative. So now the question though is this. What is the overall displacement? How do you find r? What do you use? Pythagorean theorem. 1.46 squared plus 2.85 squared equals r squared. We're looking at this green triangle right here. 146 squared plus 285 squared equals r squared. Okay? And then the last part I'll talk about in a moment. I'll let you give a second to do that.
Sorry, what would be negative?
Say it?
It would be negative 1.46.
Again, though, it's Pythagorean theorem, so the negative doesn't matter. You're squaring it, right? So why bother? You don't have to put the negative in. So I do 1.46 squared plus 2.85 squared equals r squared. Uh, 2.85 squared is going to be around 3-ish. 1.5 squared is around 2.25. No, it's not around 3-ish. I'm sorry. 2.8 squared is around 9-ish. 2.25, what do you get? 2.44. No, again. Guys, do not put the negative in. Come on, man. I just said that. You gotta listen. You're squaring a negative. So it's got to be positive anyway. So why put the negative in? You're just asking for errors. Okay, do not put the negative in. It doesn't make sense. 3.2?
Wait, what? What is that one for? The top thing, right?
Here?
Yeah.
This? 1.46 squared plus 2.85 squared equals hypotenuse squared. Remember a squared plus b squared equals c squared?
Yeah.
And that's what c is right here. That's going to be your hypotenuse. You got it?
I thought since you do negative, itself will be positive.
You got to put the negative in parentheses and then square it. You put a negative sign in front, which should be opposite after you squared it. So just forget the negative, is what I'm saying. Now, the overall displacement is 3.2 miles. But the question is, what's the angle that it's moving at? How do you find the angle? Well, think about this. Where's your starting point? Your starting point is right here. Your ending point is right here. So the object is moving which way? What's the directional? What's the directional?
South, southwest.
Good. South, then west. So if I'm looking for southwest, remember how you think of it. South of west. So here's west. Here's south of west. So we're looking at that angle right there. Now, you might say to me, how the heck are you going to calculate that, Mr. Howe? Well, there's a great fun fact from geometry. Remember parallel lines when they're cut by a transversal? Alternate interior angles. That angle right there is the exact same angle as that angle right there. Visualize, please. Visualize. Do you see it? They're vertical. Here, I'll draw on the other line. This is an extra line. Ignore it if it annoys you. Here's the other parallel line. You see the parallel lines now? You got two parallel lines coming up with a transversal cutting across. These are alternate interior angles. Okay, you could also think about these as your parallel lines up here and down here as parallel lines. But either way, those are alternate interior angles. Doesn't matter which way you look at it. Okay, so to get theta here, if you remember from class, I talked about the fact that it always ends up being tan inverse of y over x. And I didn't really go into more detail than that. But look at it. Here's theta. If you want to figure out what theta is, look at your ratio. You've got opposite over adjacent. Isn't this the y value here? It's the y value right there. Isn't this the x value? It's the x value right there. So I could say that the tangent of theta equals opposite over adjacent. Okay, again, theta's here. Opposite over adjacent. That's just y over x. So to get theta by itself, what do you have to do?
But you always have to use tangent to find the angle, right?
You don't always have to, because if you found the r value and you want to draw that in the diagram and use a sign and say, hypotenuse and opposite, you can do that. But I always use tangent. It always works, always. Okay, you could always use tangent inverse of y over x. It will always work for these diagrams. How do you get theta by itself? What do you do to get theta by itself? Right?
Like this. Did I get tangent the other side?
Yeah, how do you get rid of tangent? Do the?
Divide.
Not divide. What's it called?
It's the inverse, so it's to the negative first.
Yeah, tangent inverse. Tangent inverse. Oh, that's going to move the whole diagram, really? Oops. I don't even know where that's going to move to. I got to zoom out a little bit. Okay, there we go. So if I want to figure out what theta is, I can do the tangent inverse of y over x. Again, do the tangent inverse of this number right here. That'll give you the angle theta. That's the angle of depression, the angle at which it goes down. Okay, as opposed to inclination, or you could call it declination too if you wanted. But it's going to be 2.85 in there over 1.46. Okay, the tangent inverse of that fraction right there. That'll give you the angle at which it's moving. So whatever that angle turns out to be over right here with degrees. And what directional again we said? We're going west and then, in your case, west and then south. Okay, so it'll be degrees southwest. Do you get a number for that? What do you get when you do that? Ma, is that right? All right, that works. All right, that works. 62.9 it is. Okay? Degrees southwest. And that makes a lot of sense. Think about the answer. Okay, ready? I'm moving this way. This would be 45 degrees. This would be 30 degrees. This would be down around 60 degrees. Isn't this triangle moving down more? Look at the overall green triangle. The motion was primarily down, 2.85. Over was only 1.46. So because this is really primarily down, it means the angle is really low. So this angle is big. And that angle is around 63 degrees there. Yeah.
Do we have to put S like southwest in our as primary suit?
Yeah, I mean, if it's not,
Yeah,
yeah.
Wait, that's what
It says give a magnitude and direction to ask. Yep. A lot on that. I know there was a lot on that one question. What you need to do, and what you should practice doing, if you want to use the table method, if you've been doing fine with this, and honestly the problem set was not hard, or if the homework was not that bad for you, keep doing what you've been doing. You don't have to use the table method. The table method is just a way to organize. That's all it is. Okay, if it's the same exact approach we've been taking by looking at it algebraically and actually drawing in those triangles. There are other things to go over still, a lot of other things to go over still. I highly recommend watching the other class's video because I did not spend as much time in the other class on that question. I only spent like maybe 10 minutes. We just spent 26 minutes on that question. So I do want to point out some other stuff, but we're going to probably run out of time as to getting through everything. So I'd recommend watching their video. We also talked in 3.1 and 3.2 about these kinds of graphs. Okay, this is 3.1 and 3.2. It was all about velocity, acceleration, and time. So the primary graph that we looked at was our velocity time graph. In the first chapter, we looked at a position time graph. When we had a position time graph, we literally measured the position of the object as it moved. It would say, oh, the object's moving, then the object stopped, and then the object moved, right? When it was steady. Well, that's not the case here. So let's go ahead and draw a little bit of let's go ahead and draw a function here. It doesn't matter what it looks like. Let's say it does this. Okay? That's the motion of the object. I really don't care what it looks like, but I can talk about this a lot. What can I say in the beginning? What can I say in the beginning from here to here? What statement can I make?
Decelerating.
Good, very good. Or negative acceleration. The velocity is doing what? What's the velocity right there where I'm at? What's the velocity right there? Yeah, and then what is it doing? It's doing what? But it's moving in which direction?
Negatively?
Yeah, so you could say that the speed is increasing negatively, or the velocity itself is physically just decreasing. Remember, this graph is a graph of velocity. So when you see a line going down, think the velocity is decreasing. Yes, it's increasing in the negative direction though, okay? So you're right by saying increasing, but that's the speed. So you could say that the velocity is 0, -1, -2, -3, -4, -5. Then what happens to the velocity? It's constant. This is not steady motion or not standing still anymore. In the first test, remember this was like, oh, the guy's standing still. This just means that this person is getting more and more negative with velocity, and then the velocity remains constant for a little while. Juliet?
I don't understand how, like, if the velocity is decreasing, how does the speed increase?
Because the velocity decreasing simply means it's becoming more negative. Remember, velocity is a number line. Think of the number line in your head. When you go past 0 on the number line, aren't those numbers still decreasing actually? The word is decreasing, but yet they are increasing in the negative direction. You follow? The distance from 0 is increasing, yet the velocity itself, the function, is falling, it's decreasing. Okay? So when we say that the velocity is decreasing, it simply means that it is becoming more negative. So if I had the velocity starting here in this diagram at like positive 5 and it was doing this and falling, it's decreasing. Even when it crosses here, it's still decreasing. Only when it's moving up is it increasing. Again, speed and velocity are different entities. So yes, it's constant. Then we have the velocity is increasing. But here's what's happening. It's just becoming less and less negative. That's all that it means. So let's give a number here. Let's use 5. Negative 5, obviously, sorry. So what we can say is this. Velocity is negative 1, negative 2, negative 3, negative 4, negative 5. Still negative 5, negative 5, negative 5, negative 5, negative 5, negative 5. And then negative 4, negative 3, negative 2, negative 1. And then what happens? The velocity is 0 right here. Let's put a little circle here. Circle that, please. The velocity is 0 there. On these graphs, wherever there's an x-intercept is where the velocity is 0, because this is a velocity graph. It means that the velocity's value is indeed 0 there. And then what happens? After that, the velocity becomes positive. But this entire time, the velocity is increasing. It's going from negative 5 to negative 4 to negative 3 to negative 2 to negative 1 to 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if this is increasing in velocity, what must it have? It's increasing in velocity. What must it have? Acceleration. So that entire time, the acceleration is positive. I know that because the slope of this graph is acceleration. What's the slope of a line like this? It's positive. What's the slope of a line like this? Slope. 0. So in this middle region here, we could say that the acceleration is equal to 0. But a moment ago, you told me that the velocity was constant. Those two things correlate. Constant velocity comes from no acceleration. Again, that entire region there, the velocity is negative 5. When the velocity is not changing, you have no acceleration. What about the beginning portion? What about the beginning portion? If it's becoming more and more and more negative, the acceleration must therefore be also negative. Also, you can look. The slope of the line. The slope is negative. Slope is 0. Slope is positive. The slope of the line is acceleration. So in this region, the acceleration is negative. Okay? Again, the slope, write in big letters if you don't remember this by today. We've talked about this many times now. The slope is acceleration. What's the slope of a position graph? Velocity. Very good. Last chapter, the position graph, the slope is velocity. The velocity graph, the slope is acceleration. It's not a coincidence the way that works. It actually is, there's a reason for it. You learn more about in calculus why that happens physically. But the slopes do make sense.
I just want to visualize, how do you visualize it?
Physically moving? Alright, so I start with no velocity, my acceleration is negative. Getting faster, faster, faster. Now constant, constant, constant. It's hard to do. Let me start with here. So I start with a slow motion, getting faster, faster, faster. Now I'm at negative 5. Constant, constant, constant. Now I'm slowing down, slowing down, slowing down. Then what do? Stop at v equals 0.
Oh.
See right here at v equals 0? I'm stopping. Then what do? Turn around, and now velocity is positive, faster, 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 faster. That's the velocity increasing afterward. Okay, so this is your stopping point right here. This is your positive motion. This is your negative motion, still negative motion, negative constant motion, negative accelerated motion. This is slowing down, slowing down, slowing down, and speed. Julia, this is your kind of question, all right, that you're asking. Here, even though the velocity is increasing, you're slowing down because your speed is what's changing. That brings us back to that question. Remember that table we drew up? If you're moving this way with positive velocity and you suddenly have positive acceleration, what's going to happen? You're going to speed up. You go faster. Think about it. You're driving your car, you hit the accelerator in the same direction, you speed up. How come you can stop? What allows you to stop when you hit the accelerator? You hit the brake. The brake applies negative acceleration. So if I have the same sign, I'm speeding up. But if the signs are opposite, what do you notice? You're slowing down. It's the same thing for this direction. So I'm moving negative velocity. Acceleration pushes me more to negative, so I'm going faster, I'm speeding up. But if I'm moving with a negative velocity and acceleration is pushing back, I'm slowing down. So that table that we came up with, was it 3-1 and 3-2, that table? It's a good table to know for sure. Okay? 3-1, 3-2, and 3-4, we still haven't gone to the math of those problems. So we have to do a little quick math of those. Can I? So we have three formulas. We've got VF equals VI plus AT. VF squared equals VI squared plus 2AX. And then X equals VIT plus 1/2 AT squared. If we run out of time, I did 2 examples in the other class with these equations. Okay, so definitely look at those examples. Now, what I want to point out first and foremost, you only use what you can. So depending upon the given, you're going to pick a different formula. So the hard part of these problems is going to be deciding what is given. Is VI given? Is VF given? Is T given? Is A given? Use your units. If I see meters per second, to me, it's either VI or VF. If I see seconds, it's time. If I see meters, it's X. If I see meters per second squared, it's acceleration. The units will help you so much to determine. The only tricky part is if it's VI or VF sometimes. Is at the end or the beginning of the problem. Now you have to look at the context of the problem. It depends upon.
And don't the variables switch depending if they're calling them vertical or
Yes, so very good. That's the second point. These equations are identical. Cross off the X, put a Y. Cross off the X, put a Y. Now you have vertical motion. Exact same thing. I roll this pen across the table, I will use X in all my formulas. I drop this pen, I will use Y in all my formulas. It's the same thing though. It's the same thing. X and Y are simply just displacements. When I drop an object, what's VI? When it's dropped? 0. That's a key. Write that down. When an object is dropped, VI is 0. Did I go over the example out of my Kindle book with you guys and stuff? With an object's dropped, the person jumped off the cliff? I don't know if I did. It's too big slow to go over. It might be on the test tomorrow, that's what I'm saying. It's just something like dropping, free fall, dropping stuff.
We should memorize this, or is it on getting on the test?
These are all given. These are information. Yeah, they're always information. Remember, you have another formula that I wrote down that you're only going to use if you don't know acceleration, and that's this one. Please don't use this formula unless you're solving for A. A lot of you have been trying to use the formula in the top right to solve for VF or VI. Use this one instead. It's the same formula, just rearranged. So only if you're trying to find acceleration you're not given, and you have VF and VI, God bless you, the delta V means VF minus VI. The delta V means VF minus VI.
But like first the free fall problem, acceleration is always non-vertical.
Yeah, for an object with vertical motion, acceleration is always negative 9.81. If it's more, because it's moving which way? Gravity pulls which way? Always negative for acceleration. Okay, always negative. On the formula sheet it says 9.1, because later in here we're going to use both positive and negative. But I went over this how, in this chapter, this A and this A, when it's vertical motion, those are all negative 9.1. Guys, if you need to use the quadratic formula on a problem, which you probably will, you can graph or you can use it by using the quadratic formula by hand. Doesn't matter, whichever one you like. I went over an example of the quadratic formula in every class. Listen, today's parent-teacher conference, you're not supposed to have office hours. I'll stay after though. I mean, I'll be around still. We have like 30 minutes until 3 o'clock. The parents come at 3. So if you want to come by after school for like 20 minutes if you want more questions, that's fine. I have off periods 4, 5, and 6 today. 4, 5, or 6. So come by and meet up. And if you're 4, 5, or 6, you're welcome, guys.